Hello everyone. Today we are going to talk about bitplane slicing for information hiding. Before going to bitplane slicing, let us try to understand what is slicing. In digital image processing, slicing refers to a technique used to highlight specific range of intensity or gray level in an image. In slicing, there are two main types: gray level slicing and bitplane slicing. Gray level slicing used to highlight certain gray level or intensity ranges in an image. Bitplane slicing focus on the binary representation of pixel intensity. Now let's go a little deeper into bitplane slicing. As I already told, bitplane slicing is a digital image processing technique where each pixel of an 8-bit image is decomposed into 8 separate binary images. Those binary images are called bitplanes, ranging from bitplane 0, the least significant bit LSB, to bitplane 7, the most significant bit MSB. This allows for the analysis and manipulation of the specific contribution of each bit to the overall image.
So let's see how it actually works. First we import OpenCV and NumPy, which is needed for OpenCV to read and write images, and NumPy for numerical operations. Then we have a small function called uh, def into bit array. What it does is, for every pixel in the image, it converts the pixel value into an 8-bit binary string. So if a pixel is like 173, this function turns it into something like 10101101, and we do that for every single pixel in the image. After that we load the image. In our case it's a lina.png, and convert the whole thing into this binary matrix using that function. We reshape it so that the binary values match the original height and width of the image. Now we extract the bit planes. We loop from k is equal to 0 to 7, and each time we pick one specific bit out of every pixel's binary string. So one loop extracts the MSB, one loop extracts the LSB, and so on. Each plane is basically a black and white image where every pixel is either 0 or 1. We multiply it by 255 so that 1 becomes white and 0 becomes black. Otherwise we won't see anything. And then the code saves each plane as bitplane 7, bitplane 6, all the way to bitplane 0. When you run it, for example, and when we run it, we the code saves each plane as bitplane 7, bitplane 6, all the way to bitplane 0. Now visually you will notice that bitplane 7, this is the MSB, which looks almost like the original image because it carries most of the usual information. As we go down to bitplane 0, the image starts to look more like random noise. Next we have the code that puts the image back together using the different combination of bit planes. We again import CV2 and NumPy. Then we read all the saved bitplane images, bitplane 0, bitplane 1 up to bitplane 7. Each image is either full white or full black pixels, so we divide by 255 to normalize them back to 0 or 1. After that we create uh, we get empty result matrices like res67, res567, res4567, and so on. These will store the reconstructed images inside the nested for loop. Inside the nested for loop, we basically rebuild the image pixel by pixel. We take each bit plane and shift it left by the correct amount. Bit 7 gets shifted by shifted left by 7, bit 6 gets shifted left by 6, and so on. Then we or them together. So if we only combine bit 6 and bit 7, we get a rough image. If we combine bits 5, 6 and 7, the image becomes clearer. As we add more bit planes, the reconstruction becomes more accurate. Finally, the script saves all the reconstructed images like res 67, res 567, res 4567, all the way till res 0 1 2 3 4 5 6 7, which is the full reconstruction, and the console just prints done when everything's saved. You can see that res 0 1 2 3 4 7 resembles the original image. As we go below, the image gets start to distort.
As we seen how bitplane slicing is works, now try to understand the use of bitplane slicing. Bitplane slicing used to analyze the information structure and bitwise contribution to an image. It also enhances specific features in an image by manipulating certain planes. It is used in digital watermarking for copyright protection. Bitplane slicing used for LSB-based steganography to hide secret data. It is also used in image compression by identifying and removing less significant and noisy planes. Bitplane slicing also used in digital forensic to detect hidden data or image manipulation.
Plane slicing is used across many real-world fields because of its ability to separate important information from noise. One major area is steganography and used watermarking, where secret messages or copyright data are hidden in the lower bit plane so they remain invisible. It is also used in digital forensics, where investigators examine the low-level bit planes to detect tampered regions or hidden information inside an image. In medical imaging, bitplane techniques helps enhance subtle features in X-ray or CT scans by isolating specific intensity layers. In satellite and remote sensing, bitplane slicing is used to analyze sensitive bit-level data collected by sensors and satellites. It is also important in image compression, where the noisiest low bit planes can be safely discarded to reduce file size. Finally, in pattern recognition, higher bit planes are used because they capture the major structure and features needed for accurate detection and classification. Overall, bitplane slicing is widely used whenever precise bit-level control over image data is required. Bitplane slicing supports several powerful applications. The first is LSB watermarking. Here, hidden data is embedded into the last significant bits of an image. Because the LSBs have most no visible impact, the hidden messages blends in naturally and remains unnoticeable. Next is bit plane filtering. By modifying specific bits planes, you can remove noise or enhance certain parts of an image. For example, setting the lowest planes to 0 can instantly clean up noise images without affecting the main structure. Another important application is reconstruction analysis. By progressively adding bit planes from MSB to LSB, we can clearly see how each layer contributes to the final image. This helps us understand the importance of each bit, especially when working with compression, feature extraction, or quality analysis. And finally, educational visualization. Using a well-known test images like Lena makes it easy to demonstrate how images are stored, how bits contribute to intensities, and how the layer process works. This makes it an excellent teaching tool for digital image processing. These applications show how flexible and powerful bitplane slicing really is. Bitplane 7, the MSB, contains the highest visual contribution. It carries the overall shape and structure of the image, almost like a simplified version of the original. Bitplane 6 also carries strong information, especially facial features and major edges. Bitplane 5 and 4 contains medium level texture and soft details. As we move lower, Bitplane 3 provides very faint patterns, while bit planes 2 and 1 contain almost random looking information with very little visible structure. These lower planes are excellent candidates for embedding secret data because modifications here do not change the image noticeably. Finally, bit plane 0, the LSB contributes the least visual information. Changes made here are nearly invisible to the human eye, which makes it the best location for steganographic data heading. This comparison clearly shows how the upper bit planes maintain visual quality while the lower bit planes offer safe space for watermarking and hidden communication.
So the drawbacks and limitations of bitplane slicing are fragile data. LSP hidden data is very delicate. If the image is compressed, resized or rotated, the hidden information get destroyed easily. Filter vulnerability. Even simple noise removal filters can remove or erase an LSP watermark or message by mistake. MSP fragility. Changing even one bit in the MSP planes can noticeably damage the image visual quality. Low security. LSP steganography is well known and basic forensic tool can detect it easily. Bit management. The method needs careful handling to make sure the hidden data does not overflow into more visual bit planes. So the final conclusion will be using the Lena image. Bitplane slicing clearly shows that the MSP planes carry the main visual content. The LSP plane on the other hand are best for hiding information because they don't affect the image much. This makes the technique useful in steganography where data needs to be hidden and also in forensics and image analysis. Overall, the experiment shows how MSP planes hold the important details while LSP planes provide space for embedding information. Thank you.